I want to talk a bit about some of the research we're doing on quantum error correction using machine learning. And can you see my mouse? Yes, okay. This is work done by our esteemed chair, Dan Sahayek, contributed quite a bit, Jeremy Cote. There's a large supporting cast of students and postdocs, which you can see here. I need a new group photo after COVID is cleared up. And I just want to comment that, quantum error correction, although it's, not exactly sort of, I'd say, a topic of this workshop, I think it's something that we can kind of contribute to as a community in a very interesting way. And it also, this topic also gives me a chance to highlight contributions by a friend and great scientist who passed away last week. Many of you knew David Poulin. Pitched in better times and in undergrad with better hair back when he was, I believe, working closely with André-Marie Tremblay. So David was actually very closely connected to our community of condensed matter physicists, I would say, sort of through his sort of research network. And if any of you ever had a chance to interact with David, it was, he was a great communicator and could really sort of bridge between different worlds. And I experienced this firsthand in 2013. So some of you were at this conference that was hosted by Yingzhi and I believe Anders in Taipei, which is called the Statistical Physics of Quantum Matter. And I was working on something very different at the time, entanglement at quantum critical points. And I saw this talk by David Poulin on self-correcting phases of matter. And it really blew my mind. And it started a years-long sort of cottage industry, I guess, for me, which was, related to ideas of self-correcting and topological phases of matter, and also quantum error correction, which I want to talk about. So I'm going to introduce quantum error correction, assuming that you don't know much about it, for this audience. So if I miss something, please don't be offended for the experts. But this is very similar to how Poulin kind of introduced me to the topic way back in 2013. And I'll highlight some more features of that. Error correction. Okay, so this is in the spirit of building a computer, a quantum computer. And before we talk about quantum computers, it's helpful to pause and think about how classical error correction works. So typically, there's some, either thermal process or some external process, maybe a cosmic ray, which flips bits and can affect your computer hardware. So here I've illustrated a cosmic ray or something flipping a bit from 1 to 0 or vice versa. And classical error correction is a large industry. There's many different, ways of sort of correcting against these types of errors. But they all boil down to the basic idea of redundancy. So for example, if I encode one, quote, logical bit, classical bit, with a repetition code of 3, say, physical bits, then that cosmic ray, even though it flips 1, you can still, say that, well, 3 spins up, if you will, is supposed to be a bit on, 3 down is a bit off. I can recover that. So there's a procedure by which, we correct those errors through majority rule. And of course, if your cosmic ray flux is too high or you have too many errors, you might accidentally flip 2 bits. And then, after these errors have been applied, it's difficult to distinguish these two. It's impossible. And so then, if you use a majority rule, you'd flip this center bit back by accident. That would be a logical fault. So this idea of redundancies, error correction, and logical faults translates in a very real way into quantum hardware, except it's much more complicated. We can have indeed bit flips, but we can also have, because your qubits are prepared in a superposition state, you can also do things like flip, the sign of that second element. It's called a phase flip. And in fact, if you think about it, you could have sort of any sort of unitary rotation. You could also have mixing with the environment. You could have thermal mixing that can be modeled and so on. So there's many more ways that qubits can be affected by errors. And also simple error correction like these repetition codes aren't possible because of the no cloning theorem. And further, we really can't do projective measurements and preserve quantum states. So we need to kind of overcome all of these challenges in order to design, the equivalent for quantum hardware, the equivalent idea of error correction that we have for classical hardware. So quantum error correction is just this idea that we're protecting against noise, whatever that noise is, coming and influencing either, our qubits, either from the environment, or, it's not just our qubits. It can also be the gates that we apply, the single or 2 qubit gates, for example. If you just think about a quantum state and its stability, that's typically called a quantum memory. If you think about applying operations on it, right, that's a whole nother problem, which, if you can control all these errors, leads to this idea of fault-tolerant quantum computing. So the idea that you can, perform operations on in a quantum circuit, without errors propagating or proliferating, I should say. So many schemes are devised. I mean, these go back decades. Famous names like Ray LaFlamme and so on. Shor's code is probably the first one. And I just threw a couple of figures up that I pulled from David Poulin's papers. And I mean, he contributed to many different sort of paradigms in quantum error correction, including CSS codes, polar codes, low density parity check codes, which he was working on, which we were talking with him about in the last few years. And what I'm going to talk about, which is topological sort of error correction. So by the way, this is a hashtag that's trending on Twitter. If you have any of Poulin's greatest hits, I encourage you to tweet about them so we can all share. And it's a very theoretically interesting subject. There's a lot of great sort of theory and numerics behind it, but it's also, maybe for this audience, relevant as an experimental topic, especially in light of these so-called supremacy experiments by Google, which came out recently. Actually, when I was visiting CCQ last winter or fall there. So this is just an image of Google's supremacy circuit, this 53 qubit circuit, where qubits are crosses and the couplings are these squares with the error rates illustrated. And I'm not going to talk about the supremacy experiment, but if you read this paper, you'll see that they mention that the architecture is suitable for error correction with a surface code, and I want to talk a bit about that. They also mention that there's a target error rate, so a single qubit error rate, which is are these numbers in isolation or have a certain target for these hardware manufacturers, and you'll see why in my talk. So the surface code, which was mentioned in that previous slide, is really just a variation of something we're probably familiar with, which is Kitaev code, the Toric code. And I've drawn it slightly different here, so there's different ways of thinking about it. But I wanted you to imagine a square lattice that's embedded as a torus in higher dimensions. So I'm connecting, for example, this, let's call it edge to this vertex, and so on this edge to this vertex here. Kitaev's Toric code has degrees of freedom, which okay in this representation. So there's qubits, so there's spin 1/2, if you will, objects sitting on all of these edges. And these qubits interact with a Hamiltonian that has 2 pieces, a vertex and a plaquette piece, sometimes called. So the plaquette piece is the product of all SZ, Pauli operators around that yellow square, and the vertex is the off-diagonal piece in this language, which is the product of sigma x's around that green cross. And again, this is kind of a a standard model for quantum spin liquids, topological order, Z2 spin liquids, and so on. And I'll slip in and out of that language, and also the quantum error correction language, which calls these operators either check operators, or I'll probably just use the word stabilizer for these operators, and we'll see why in a minute. So to understand the ground state of the Toric code, I mean, there's many ways to do it, but one way that I find useful is to sort of come from this, I'd say, classical limit, or else this idea of having a preferred or computational basis. So let's imagine that I'm looking in this sigma z basis, which has eigenvalues, spin up, spin down, or whatever we want to call it. The the stabilizer generator or the plaquette operator in that Hamiltonian, let me note there's a minus sign in front of it here. If I just consider that piece in isolation, then the low energy state of each plaquette is degenerate. Okay, so it's one of these 8 different possibilities where I have an even number of plus and minuses, essentially, right? So that gives me an eigenvalue of this operator, which is +1. And if you decorate the entire lattice with these +1 operators, that's the kind of classical ground state of the Hamiltonian in the limit where only this B plaquette operator acts. If you have an odd number of, say, spin ups or an odd number of spin downs, I mark these plaquettes with an X, which will become relevant in a minute. And really what that is marking is a violation of this will or an energetic excitation, indicated by this minus eigenvalue. So in the classical limit, in this basis representation, where I just have this plaquette operator, you have an extensive degenerate manifold of states where each plaquette obeys this constraint. Now, if I add the second piece of the Toric code, which is the vertex piece, what you'll see here is I've actually operated on one of these classical configurations with the vertex, which flips spins. So this is sigma x, which basically flips in this basis. All the spins to these white or minus configurations. But what you can see is that there's no violations of the plaquette constraint. Okay. So what this does is take you from another classical ground, from one classical ground state to another. And by these operators commute in the end. And so what you can imagine the ground state of the Toric code being is an equal amplitude superposition of all possible, plaquette non-violating states. So that's one way to think about it. And of course, there's other ways of thinking about it. The final thing I'll say is that we know this is a sort of model for Z2 spin liquids. In the topological language, for topological quantum computing, we've encoded now, we've used the redundancy, just like in the classical repetition code, to encode 2 qubits in the Toric code. And if you're familiar with the concept of topological order and winding numbers, this is very closely related to the qubit operators. So we have another operator, which is, I've written it as a Wilson loop for the Z operator of all possible, of sigma Z operators, which wrap around the lattice in this configuration. And your X, operator for this, what I'm calling a logical qubit, the larger qubit, is the blue and vice versa. So the idea is that the idea behind the surface code is to use the sort of topological order of the Toric code to encode, in this case, 2 qubits out of many physical qubits which are living on the edges. And the reason, there's many reasons, but the main reason is that the topological order, or for example, the topological number that's measured by this Wilson loop, this operator, is stable to local perturbations. And that's kind of the key behind quantum error correction with these codes. So those local perturbations, we can study those kind of number one in isolation, and then how they all pile up. And that's kind of the idea of modeling errors, or error channels or things like that. And again, as I mentioned, there's many different errors which can occur. And if we just restrict ourselves to sort of poly operators and sort of the simplest possible cases, the simplest case to imagine is just this bit flip error. So local error, which applies to what I'm calling a physical qubit, which flips the state. And so if I'm looking in this classical picture where I've maybe done a projective measurement and measured the state of my lattice, this error is just the sigma x operator operating to give me a bit flip, in some sense, which is a single site or a single physical qubit. And therefore, after that error operates, I actually get 2 violations of this constraint on the adjacent plaquettes of the sigma z stabilizer. But of course, one point that I'm trying to get across is that in quantum error correction, we don't have access to we can't perform projective measurements on all qubits in any basis, or we destroy, of course, the quantum nature of the state. So really, we shouldn't be thinking about the qubit degrees of freedom at all. We just know that they're sitting on the edges of this lattice. And if I have a sigma x bit flip error, as long as I know the lattice site that it applies to and the nature of it, so if I'm modeling it with a sigma x operator, then all I need to know is that there is an error which has been applied to that qubit. And the presence of that error is detected via this stabilizer measurement, which I'm now going to imagine that we're taking all the time on this lattice, which will produce two x's. So I'm calling an x, a violation of the stabilizer, which we saw previously. And the point is that these stabilizers can be implemented experimentally. So I encourage you to look at this paper of Austin Fowler's from 2012, which really laid out kind of, I think in a very clear way, how this type of idea is implemented in hardware. And it's done via an ancillary qubit for every stabilizer, for every plaquette on this lattice. And this is just another drawing of the X and Z stabilizers that I showed you before, with the control qubit and with CNOT gates. And what this allows us is to essentially non-destructively measure these stabilizer operators without sort of resorting to projective measurements of individual qubits, which again would destroy the state. Giacomo talked about process tomography on these types of circuits. And so we can imagine not only kind of errors that occur within the state, but we should also imagine errors which occur for different elements of this circuit, and those could be in principle measured for individual stabilizers with process tomography, and those could be input into any sort of quantum error correction. So you can see how you have different errors which could occur in the state itself, and then you can have errors which occur in the stabilizers, the application of the stabilizers which produce the syndrome, and you can, at every stage of this game, you can imagine putting more and more errors in and asking sort of, can I correct for those? So this stabilizer formalism, by the way, which allows for this non-destructive error detection, which is the basis of this talk, was fleshed out largely by Dan Gottesman at Perimeter here, and also David Poulin had a greatest hits back in 2005 when he kind of generalized the stabilizer formalism. Another great paper. So let me imagine that I have let me imagine that I know where the errors have been, where the errors have occurred, which is kind of the perspective I've been taking. And let me imagine that I can produce perfect syndrome measurements. So what I've just convinced you, however, is only the latter is technically possible, right? I can't, in principle, how do I measure an error? It's through the syndrome. So really the X is the thing that's going to be measured. Sorry, I was trying to go backwards, by this circuit here, that orange X. But the goal is that, by looking at these two positions of the syndrome, I actually know where that error is. So that's what tells me where that red error is. And what I can do is then apply a recovery operation. So for example, that Z stabilizer, or that BP stabilizer, what I called it, the plaquette stabilizer, will detect the presence of a bit flip, which is what I just showed you. And so we can perform what's called a recovery operation by essentially flipping that bit back. So the kind of game becomes, looking at the syndrome and then applying recovery operations so that when I do so, everything returns to its previous, if you will, state. And since I'm not looking at projective measurements of individual qubits, this is kind of the information that I want. I want I want this topological order, if you will, or this topological sector to be preserved by the recovery operation. And so the problem becomes, or the redundancy happens, when you have chains that look like this, okay, where really all you have access to is the syndrome at the end of the chain, which is where an odd number of qubits has been flipped, right? So it actually looks like this. And then as you can see, there's many redundant ways to correct that syndrome. So if you find a recovery chain, something like this, and you don't have access to the error chain, you better hope that somehow you haven't flipped the logical qubit. And in this case, where I have this sort of trivial loop which doesn't span the lattice, you can convince yourself that in this case, the logical Z, if you will, operator defined by this orange Wilson loop is preserved because what you've done is you've flipped a pair. As long as you flip an even number or apply the error to an even number of, if you will, spins on this lattice, the logical state is preserved. And then, of course, the problem is if you have an error chain like that, which again, the red is invisible, all you have is a syndrome. If you apply a recovery chain that loops around the lattice with respect to the original error chain, which is unobservable, then you'll get a logical fault. Because what happens with this Wilson loop, the logical Z operator, is you flip, the parity of it, essentially. And the parity of that operator is really what defines your topological sector or your topologically encoded qubit in some sense. So you want to avoid those logical faults. And what you're really looking at is errors that look more like this. Instead of having an isolated pair of syndromes, you basically can imagine at least local errors in this model occurring all over the lattice with some probability. And this is the error model that I'm going to use now. And so what we have is this so-called syndrome, where we look at a whole bunch of these X's and we ask, what is the recovery chain? And the goal of a decoder is just a classical program that suggests a recovery chain without producing the logical fault like I showed you. So this is an important application of basically classical computing for fault-tolerant quantum computing. So there's many possible different ways of doing this. I mean, how do I choose the recovery chain is kind of the question. The first proposal, which was in this classic paper, which is very powerful, is minimal weight perfect matching, where you just find this, the shortest error chain between the syndrome ends. Hopefully it's the right one. But I also want to point out that there's many different ways of devising decoders and based on different principles. And two fascinating ones are, of course, tensor network, basically error correcting decoders, and also RG based decoders, again, which were developed by Poulin over the years. So there's really a large kind of amount of work along this direction. And machine learning can be used to define a decoding procedure. And so what I want to talk about for the rest of my time is sort of how we turn this into a machine learning problem. So the first machine learning quantum error correcting code or quantum error correction procedure was, basically thrown on my desk by our esteemed chair back in 2016, 2017, and it basically involves our old favorite, a restricted Boltzmann machine, so a generative model. And we've seen a lot of talks about restricted Boltzmann machines, so I'm not going to go into details, except to point out sort of how the generative model structure allows us to do decoding. So again, a Boltzmann machine is a joint distribution defined by an energy. Here we have two different weight matrices between a hidden layer and two visible layers, one for the error and one for the syndrome. Okay, and there's weights and there's biases and so on. And so we can imagine training the weights and biases with data to sort of give a joint distribution that relates syndrome to errors mediated through this hidden layer, which is, of course, you could vary in size. Oops. So training a sort of any generative model decoder just involves feeding in, we know syndromes and we know errors. So in the training set, we assume that we can basically figure out the error chains. And what we want to do after training is, attach this thing to a quantum computer, read out the syndrome locations, and suggest a recovery chain. So that's the kind of the generative modeling step associated with this. And, there's a lot of detail. Read the paper, which goes into this. But the bottom line is that, you can characterize the performance of these decoders, which are trained on data. So this is a data-driven thing. You have a separate program which produces syndromes and errors, right? So this training set is produced, right now we do a synthetic, we do it synthetically with other types of simulation methods. But eventually you imagine you have a trusted piece of quantum hardware which produces syndromes that you can essentially train this thing on. And this data-driven technique can be compared to other methods like minimal weight perfect matching, which Giacomo did in this paper. And you'll see curves for different sizes of toric code. So this is a 4x4x2, I guess, 6x6x2, which look like this. So how do we measure the performance? It's by keeping track in the test set, if you will, of the probability of a logical failure, as a function of the amount of errors which occur on the lattice, or the probability that a bit flip error occurs. Okay, and you see curves like this. We did it for 2 different sizes here. And what you're seeing is that for low probability of error, for kind of a sparse scattering of the syndrome, you get a low probability of logical failure, and of course this takes off. There's some discrepancy, or some difference, I should say, between the NED, which is the neural decoder, which is the one trained on data, versus the minimal weight perfect matching, and they are different decoding schemes, so that's not surprising. So, but what is also important, which I want to point out, is the idea of a threshold. And the threshold is the kind of reason behind the desire for low probabilities of single and double qubit errors in the hardware. So when Martinez and those people say that we want errors below a certain number, it's really because there's something that's called the threshold that exists. And the threshold, it's in a dual language. You can map this model to a random bond Ising model. It's known to be a phase transition, and this would essentially be an order parameter that in the thermodynamic limit would jump between 0 and 1.
Roger,
so that
5 minutes.
Yeah, so that says that, in order to produce fault-tolerant, like true fault-tolerant quantum error correction in the thermodynamic limit, you have to be below this thermodynamic threshold. And again, this is something that can be mapped for many of these simple error models to a statistical mechanical system. So the concept of a threshold is really important, and again, something that we can relate to condensed matter and stat mech. So just a few points. General challenge is that these recovery chains suggested by this type of architecture, I've just flipped it on its side. You can imagine, there might be some imperfection in the learning procedure, or some limitation of training data, or something like that, which introduces biases. These biases can result in error chains which don't match the original syndrome. And this was observed to be a major loss of efficiency. And all I want to say is that, we're starting to explore different generative models where this efficiency can be addressed. And one of those is the recurrent neural network, which Quan talked about. I won't go over it here, but a couple of points that Quan mentioned. An RNN has this, through this chain rule, you can express the probabilities of sampling errors now, not qubit state, but errors, as conditional probabilities through a joint distribution that's normalized and has this autoregressive feature. Another thing he just mentioned briefly is that symmetries can be imposed. And we've been hearing a lot about the importance of symmetries. And just to flash this up, the work by Jeremy Cote recently was to implement symmetries into the recurrent neural network for the purposes of error correction. So the symmetries we're interested in are really the Z2 gauge symmetry, right? It's a local gauge symmetry that tells you, if you don't have a syndrome, that your plaquettes, that your plaquettes have to have a certain, they have to be part of this ground state manifold. And if you have a syndrome, they don't. So the RNN in this quantum error correction procedure is a sequence that's mapped, just like Juan said. You snake through the lattice in a certain way, like you would do for 2D DMRG. And as you're training and as you're sampling, you can implement a check on local symmetries, in this case, which preserve sort of the syndrome. And just a word on results. This is a different configuration. This is a rotated Toric code, so these numbers don't match with the numbers you've seen before. But as I go from some system size to another, this is the probability of accepting a correction chain, an error correcting recovery chain, which means it obeys the syndrome. And so as you get larger and larger, you start to, in terms of lattices, you start to see the inefficiencies creeping in, which can be corrected by implementing symmetries in the recurrent neural network, bottom line. And then you get pictures that look very similar to what I showed you before for the probability of logical fault versus the error model. And you can see the position of the threshold there. So we've done a lot of work on Toric codes, you know, surface codes, where there's, you know, probably machine learning isn't beating conventional methods. But I just want to mention that David Poulin picked up on this idea, you know, almost immediately, and we had discussions ranging back to 2017 or earlier about where this type of sort of machine learning paradigm might actually make a difference. And I would say that he proved this in this recent paper in 2019 with so-called, you know, local density parity check codes. And he showed that, you know, training, that there's some mapping to neural networks, and training actually substantially improves the performance of these so-called belief propagation decoders for a family of codes. And so, you know, I think in this field, we're always looking for, you know, greatest hits, or you know, we're looking for where machine learning has made a difference. And I really believe that in the arena of quantum error correction, Poulin showed, you know, just last year, that there's really potential for machine learning applications to make a difference. So I'll leave it there. I'll leave this up for questions. I just want to emphasize that we've just scratched the surface. There's many different errors. There's errors in measurements, and there's also many codes that these can be applied to. In terms of thermal quantum, self-correcting quantum memories, which is something that I've been interested in for years with Hastings, we can possibly apply machine learning. And you know, one of the strengths is really that it's a data-driven paradigm. So if we can produce syndromes and errors, we can train these very general decoders, which really can be translated between different applications. But I think the main point is, like, you know, it's conferences just like this where I think a lot of ideas can kind of transition between fields. And David Poulin really took, you know, the idea of quantum error correction and kind of gave it to me in a gentle way that I could understand back in 2013. So in some real way, you know, this whole field now of quantum error correction with machine learning is just another one of his greatest hits. So thank you very much.